there's a formula that can be used, but let's try to make some sense out of it, try to wrap our minds around it a little bit. We begin by solving for P in the compound interest formula. So we've got the regular compound interest formula, and we're solving for P, okay? And maybe it's not totally obvious how this is happening, but what we're really doing here is multiplying both sides of the regular compound interest formula by, well, by the negative nth power of 1 plus I. Okay, so 1 plus I to the negative n. And then if we do that over here, 1 plus I to the negative n. Now, all of this cancels. Okay, you might have to renew, go over your old rules of exponents to see exactly how they cancel, but they do cancel. And so all of this stuff here is going to cancel. And we're just going to be left with P. Okay. And of course, this is the other side of that equation over here. So there's a formula. Okay. But notice we started with P. We begin by solving for P. What is P for a compound interest problem? A regular old 3.2 compound interest problem. P is the present value, right? P is the present value. We call it principal in those problems, but it's a present value. A is the future value. And we're just kind of extending that problem. Okay, so the first 4 payments, we don't know what they are. We're trying to figure that out. What is the present value of this? Annuity that is going to do this, allow us to make these withdrawals, which from the bank's perspective are payments of $3,000. Okay, and so using the formula that we just had, which is just the old compound interest formula, but we solve for P, these are the payments. Now this is the formula, of course, 4 times. And we could do it 4 more times, and that would be all the times. Okay, 4 times, 4 more, that's a whole year, right? That's 4 quarters. And then we could do it 4 more times for the next year. And as Barnett says here, we could proceed to calculate the next 4 payments and then simply find the total of the 8 payments. And that would be your total present value. There are 8 payments, since there will be 8 total withdrawals. Okay, so if you're the borrower, in this case the institution to which you are making the investment, they are, from your perspective, they're going to be withdrawals because you put in your money and now you're going to get payments made to you. So 8 withdrawals. This method is tedious, though. We could do it. We can kind of understand it too. The actual formula, though, we just want to understand it as a logical extension of the experiment that we're doing. So here's our formula. Here's a formula, and PV, present value of all payments. Okay, so this is, if you added P1, P2, P3, P4, P5, P6, P7, P8, that would be this PV here. Payment is periodic payment, okay, quarterly, in this case 3,000, and we get this expression as a coefficient. I is the rate per period, N is the number of payments, the familiar definitions. Payments are made at the end of each period because it's an annuity, and that's the defining characteristic of annuity. So back to the original problem, how much money must you deposit now at 6% interest compounded quarterly in order to be able to withdraw $3,000 at the end of each quarter year for 2 years? Okay. And so we're just going to use the formula. Now, this kind of goes to another problem that came up, which was the problem of the letters that are used for the notation in the finite math review card as opposed to the text. But this P here is present value. Okay, so right there we've got present value, and R is the letter chosen for just the payment, right? That used to be PMT, or payment. And we're just substituting things into the formula. Payment, the 3,000, that's going to go in there for R, and the I, we had a 6% interest rate, interest compounded quarterly. So do that division because I equals R over M, right? We remember that, don't we? I equals R over M. Rate per period. And total number of payments is 8. So substitute all of those values in and we get this expression. And of course we got to be careful when we go to the calculator with all this. Barnett does a great job of talking about that. But the result is 22,457.78. Now that's an interesting number. Okay, that is the answer. So we don't want to, get lost here and lose that fact that this is our answer to the problem. How much money must you deposit now at that rate for that compounding period in order to produce that result, $3,000 withdrawals? You have to deposit $22,457.78. Okay, now that's an interesting number. We're done with this problem, and there's another problem to talk about. But why is that interesting? Well, consider this new problem: interest earned. How much interest was earned when we did all that? Okay, so this was the present value. That was the answer that we just got. Total amount of money withdrawn over the 2 years is a larger amount, 24,000. Okay, so 3,000 quarterly, 2 years, multiply all that, 24,000. Okay, is the total amount of money withdrawn. So you can see how this is an annuity because you're going to withdraw more than you paid in. And you paid it up front, so the present value of the 24,000 that would eventually be withdrawn was less than that, 22,457.78. And we could also talk about the amount of interest earned, which of course is the difference, 1,542.22. And so we're kind of starting to understand the idea of present value as opposed to future value. And Barnett gives us a helpful strategy for solving mathematics and finance problems. Determine whether the problem involves a single payment or a sequence of equal periodic payments. Okay, so when you see that, a sequence like that, you know you're talking about you're talking about an annuity. When you see sequence of equal periodic payments, okay, you're talking about an annuity. Okay. If it's a single payment, then that might have been a simple interest problem or maybe a compound interest problem. Simple and compound interest problems involve a single present value and a single future value. Ordinary annuities may be concerned with a present value or a future value, but always involve a sequence of equal periodic payments. If a single payment is involved, determine whether simple or compound interest is used. Okay, so 3.1 in Barnett, 3.2 in Barnett. Simple interest is usually used for durations of a year or less, and compound for longer periods. Now here's the interesting thing to us. Step 3. If a sequence of periodic payments is involved, determine whether the payments are being made into an account that is increasing in value, a future value problem, or decreasing in value, a present value problem. So that is, we can see why this is a really helpful statement. Okay, so increasing in value, that's 3.3. Future value, you know, we're paying every month, and then at the end, boom, huge payoff. Okay, so increasing in value, future value. But then we get the problem that we just had. There's a principal or a present value that is paid, and then after that, the account, the amount in the account is decreasing in value. That's a key word, okay? Account. What's happening with the account? Always think about that, okay? Right? In the present value problem, the account starts off big and then starts to decrease in value. In a future value problem, you know, it's the amount in the account starts off little because you're just making little payments and there hasn't been any big payment, any lump sum. So it starts off small, but then at the end it gets to be huge, big old payment. So always think about what is going on with the account, and that's how you're going to be able to tell the difference between future value problem 3.3 or present value problem 3.4. Ask yourself, what's going on with the account? Key word there, account. If the account is increasing in value, it's a future value problem. If it's decreasing in value, present value problem.